90. Okay, good afternoon. Let us start our lecture. Okay, so we start talking about how to estimate a parameter of a given distribution. So estimators. So there's two properties about estimator that we would like to look at. One is unbiasedness, which means that an estimator, we have a parameter, theta, and we have estimator, theta hat. And remember, this is a function of, so if I write it like that, all right, so it means that this thing is a function of the random sample x1 up to xn. Example is x bar. Another example is the sample variance. Maximum of xi is another example of estimator or a function of the random sample. So unbiasedness or unbiased estimator satisfy that the expectation of the estimator equal to theta. And the difference is called bias. Theta hat minus theta. So if this difference equals 0, then this estimator is an unbiased estimator. All right? Of course, there's another one that okay. So there's another quantity, is the variance that we would like to look at. So we would like to compare two estimator and look at their variance. So of course, the one with the smaller variance supposed to be better. All right. Okay. Although it's not in the notes, but I briefly talk about mean square error. Oh, I forget about it. Okay. So then, besides just have a point estimator, we also would like to look at an interval, to give an interval. All right? So these estimators are random variables. So the interval, we also want to, both ends are random variables. So I denote it by something like this. All right? So an example for confidence or for interval of to estimate theta or mu, then we will have something like this: minus 1.96 sigma over root n. So this will be our lower limit, and this will be our upper limit. Both are random variables because they are functions of x bar. This part is assumed to be known. You know 1.96, right? Sigma is supposed to be known. If it's not known, then we cannot use this formula or use this as a... if it's unknown, then we have problem to evaluate this confidence interval. All right? So why I have to pick that? So can I change this to 1 instead of 1.96? Yes, you can do that. Then what's the difference between the two? All right? So basically this simply saying that this random interval covers the unknown constant mu, unknown parameter mu. All right? So we would like to know what is the chance that this covers. So compare with this. Plus 1 times sigma over root n. Which has a bigger probability? The first one or the second one? Which one? This one? Or this one? The first one, right? Why? Why? Yeah, it's bigger, wider. What is the length of this random interval? So this minus this is the length of this interval, the what I write down for A, this interval. Is it fixed? The width. Is it fixed? Yes. Is it random? No. Why is that so? I thought I say this is a random interval. All right? Basically, because the x bar cancels out. So this interval depends on what your x bar is. So it may be here because your x bar is here. All right? But if your x bar is here, okay, I just distinguish it, so that's why I make it another one as upper level, right? So the width here is the same as the width here because both have the same width, which is 2 times 1.96 times sigma over root n, right? While this width is shorter, right? So a bigger, a wider interval should have a higher chance to cover the unknown parameter mu. So the A interval A should have a bigger probability. All right. So how to get this? So we can use this knowledge about x bar. So remember, if the data is from normal, x is from normal distribution with mean mu sigma square, then x bar minus mu over sigma over root n is standard normal. This is a random variable, this is the distribution. Now this is what we are going to discuss today for other problems. So the idea is that I get a quantity or a random variable which involve the mu. And the rest is either a random variable which consists of, which is a function of the random sample. In this case, it's x bar. Then the rest of the expression can be obtained or calculated or known. So here I must assume sigma known. If sigma is unknown, then I cannot use this formula. I will discuss it later when the case sigma is not known. But if sigma is known, then naturally I can establish that, okay, x bar minus mu sigma over root n between two numbers, standard normal, two numbers, such that the probability falls in between these two numbers is, let's say, 95%. So what is this number? This number, we have a notation. Lowercase z, 0.025. The subscript 0.025 means that the probability of a standard normal random variable greater than this value is 2.5% or 0.025. So because standard normal is symmetric about 0, so this is minus that 0.025. So in other words, it's between these two numbers, minus 0.025, between these two numbers, what can we say about the probability? So the probability 2.5 here, 2.5% here, so false in between this should be 95%. All right? Then, remember, this one basically means that you have two inequalities, 1 and 2. So now, in order to find the confidence interval, I just have to replace or try to work it out so that instead of something like that, I change the two inequality so that mu, just mu, find mu, because mu is the one that we try to look for estimator or confidence or interval estimate of mu. So mu in the center. And the rest, put it on the other side of inequality. So from this part, we can rearrange it so that it is x bar plus z 0.025 sigma over root n. All right? And then from this part, rearrange it. So we basically multiply z over sigma over root n, and then add sigma there, and then change it to the other side. So it's 0.025 sigma over root n. And the probability of this one is 0.95. So now this is my confidence interval. This is an interval that I believe the chance of this random interval cover the unknown mean with a probability equal to 95%. All right? So we call this, we have a name for this. We call it confidence level. All right? So this is the formula that you see frequently. How to get this formula? What are the assumptions that we make? Does this formula, this confidence interval, apply to any problem concerning about mu, population mean? Or in other words, is this always true? Sample mean minus mu divided by sigma over rho n. Is this random variable, or does this random variable always follow a standard normal distribution? No. Only two scenarios that this is true. The first one is that the underlying distribution, that means you are taking a random sample from a normal distribution with mean, mu, and sigma square. That means we required that the population follows a normal distribution with mean, mu, and variance sigma square. What's the second scenario that I can use this? I can accept this, or at least approximately. So the other alternative is, the other scenario that this is true is that when sample size is big, right? When sample size is big, we use a rule of thumb as 30. So when the sample size is bigger than 30, then we can apply the central limit theorem. Then x bar, okay, so I don't know the distribution of this random samples. All right, but I know that expectation of xi is mu and variance of xi is sigma square. All right, then x bar minus mu over sigma over root n will be approximately follow a standard normal. So that I can proceed to do the same job, so this will hold. All right? Okay? Now, what happens if sigma is not known? Can I still use this formula? What I mean is that use this and this as the confidence interval or interval estimator for mu. Can I use that? So I draw a sample. I work out the sample mean, work out the sample variance. Can you use this formula? Strictly speaking, you cannot. This formula needs to know sigma. Is sigma the same as sample variance? Sigma square and S square, are they the same thing? No. Sigma square is a constant. about the population. Although we don't know, but there's a constant. While S square is just the sample variance. Depends on your sample. Different sample will give you different value of S squared. So S squared, in fact, is a random variable. All right? It's a function of your random sample. So it's a random variable. So S squared is not as sigma squared. But there's some confusions. So sometimes when the sample is big, then we can say that the S square is quite close to sigma square. So we can use it. But remember, it's only an approximation. I'm not saying that S square equal to sigma square. I'm just saying that because the sample size is big, your S square, the sample variance, is very close to sigma square. So I replace the sigma square by, or estimate the sigma square by S square. All right? Okay, so now, if sigma is not known, then what to do? So if sigma is not known, so we cannot sit there, so we'll replace the S by something that we can obtain or calculate from the samples. So we'll use this one. Replace the sigma squared by S squared. Then the next question is, what is the distribution of this one? Remember in chapter 5, we discussed it. This one is a T distribution with n minus 1 degrees of freedom. All right? So in other words, now we look at a T distribution with n minus 1 degrees of freedom. I can look for two values. T, what's the notation that I use? Okay, I'm sorry, sometimes there's some confusion. So I try to write it in the notes. I use this, T with A, T with the degrees of freedom, and then with alpha. All right, so there are two parts of the subscript. The first one is referring to which distribution we're talking about. All right, so the degrees of freedom. The second one is the probability greater than this value, or on the right-hand tail or the upper tail. So in this case, I write, if I want 95% confidence interval, or interval that I have quite confidence that this will cover the unknown parameter, all right, this random interval will cover the unknown. So I choose 0.02, n minus 1. This is the degrees of freedom, and 0.025. So therefore, this is 2.5%. While this one, reflect it with 0, so it's minus n minus 1, 0.025. All right? So this also 2.5%, less than it, bigger than it. So somewhere in between, this is 95%. So now I can write down x bar minus mu s over root n lies between these two numbers, n minus 1, alpha over 2, and this side, Tn minus 1, alpha over 2. Now I can do that because the T distribution is symmetric about 0. So the value, this Tn minus 1, 0.025, greater than this value is 2.5%. So if I reflect it to negative on the negative side, so less than it is also less than minus 2 Tn minus 1, 0.025 will be also 2.5%. All right? So the probability that this one is equal to 1 minus alpha. So alpha over 2, so in the center will be 1 minus alpha. Because the alpha, you have two parts that is not yours. Each is alpha over 2. Combine them will be alpha. So the remaining one will be 1 minus alpha. All right? Same story, rearrange it so that mu in the middle. So for example, look at this part. So I just multiply this with s over root n. All right? Tn minus 1 alpha over 2 s over root n. It's supposed to be on this side of the inequality. Oh. So now, and then I move the mu here. Okay. So I move it to the other side, so it becomes minus. Then x bar minus mu, I add mu, so that the mu is here. X bar, no change, it stays there. All right? From this inequality, I got this inequality. Right? Just rearrange it. Just remember, you try to arrange it so that mu is on one side of the inequality, then the rest of the term try to move out to the other side. Huh? So similarly, for this part, that will give you x bar plus Tn minus 1 alpha over 2 s over root n. And the probability of this one is 1 minus alpha. So you can see that the formula is very similar to the previous one when sigma is known. So when sigma is not known, I replace or estimate the sigma by S, by the sample information. By doing that, it's no more Z alpha over 2, but instead I take this constant from the T distribution. So it's Tn minus 1 alpha over 2. All right? Okay, so this is the confidence interval when sigma is not known for mu. So what assumption have we made in order to use this formula? Do I need to know sigma? No need. I don't need to know sigma. I just use the sample variance. Do I need normal assumption? Does this follow a T distribution? This comes from the sample, the population is normal. So you need the normality assumption. But we can, so this result needs normal assumptions. All right? Now, but what happens if your sample size is very big? Sample size is very big. All right? Then this, when n is very big, this approach to a standard normal distribution. So in other words, if your sample size is big, all right, then I can replace this by Z alpha over 2. If n is big, so this is what we mean by big. It's not 100, maybe not 1,000. It's just a big number. All right. Of course, in practice, we just maybe 30. Bigger than 30, we consider it big. All right. So we can replace this by Z alpha over 2. So, in other words, I will use this formula all right, or use this as my confidence interval if you have big samples. All right, all this discussion still assuming that the population is normal. Okay? Now, what happens if the population is not normal? All right? What happens if the normal distribution assumption is not valid? Can I still use this formula? Yes, only an approximation. Why? Let's go back to the central limit theorem. The central limit theorem saying that you don't know what the distribution it is, but this sigma over root n is standard normal, right? Approximately. Approximately. All right? Now, so if n is bigger, this S square is very close to sigma square. So if your sample size is big, then I can replace this. I still consider, of course, the approximation may be not as good as the original one, but this one is approximately normal. All right. Okay. So that's how we do things. Let me summarize it again. Our objective is to find an interval, a random interval, to estimate mu. Okay, so start with is that, okay, the population. If the population follow normal distribution, so know this information. And another piece of information, if you are told that, what is a sigma? That means sigma is known. Then under this, with normal assumption, that means the data are from normal distribution, and with sigma known, then my confidence interval will be like this. I will use this. All right? This is something to do with the standard error of x bar, and the constant is taken from a standard normal. All right? So, even if the sample size is not, even the population is not normal, I apply the central limit theorem, I can still use this formula, or this interval, right? Use this interval as an approximation. All right? And why we can do that? Because of the central limit theorem. We are not working on the x. We are working on the x bar, which we know that it follows approximately standard normal after we adjust it. So just now I also mentioned, okay, what happens if I don't know sigma? So if I apply the central limit theorem, I can replace this by the sample variance. All right? So you have to understand that I can use this. All right? This is the last one that we just talked about. Then I use this mu is between x bar minus z alpha over, plus z alpha over 2 s over root n, and x bar minus z alpha over 2 s over root n. So this one is approximately equal to 1 minus alpha when the sample size is big. All right? But if the sample size is not big, then you better use this t n minus 1 alpha over 2. All right? But if you use that, you have to remember, you require the distribution of the population has to be normal. All right? There are no central, because the sample size is not big, we cannot use the central limit theorem. So in that case, you need to have the normality assumptions. If you don't have that, then we don't know whether this one is correct or not. But if your sample size is big, then we can apply this central limit theorem, at least get an approximation. Okay? So these are all the background or the foundations. Now we start to run. All right. Okay. So now we start to talk about confidence intervals for the mean mu. First case, variance is known. Sigma is known. All right? And the population is normal. All right? That means all the x are normal distributed. Or at least the sample size is big. All right? Then, Okay, this is what I just mentioned. X bar minus mu over sigma over root n is standard normal. All right? Now, it's important that we get this quantity. In this case, it's the x bar minus mu over sigma over root n. This quantity is used to derive our confidence interval because it involves mu. Mu is the parameter that we want to estimate. And on the other hand, it also involves a random variable, which is a function of the random sample, x1 up to xn. In this case, it's the x bar. And the rest of the expression is just a constant. Because sigma is known, so it's a constant. So now I know the distribution of this quantity or this random variable, and then I can write down this statement. All right? These random variables between these two values, remember, this is the value, and this is the value here, so that this is alpha over 2, and this part, this area is also alpha over 2. All right. So that in the middle is 1 minus alpha. Rearrange it. So this is my confidence interval. Lower limit and upper limit. All right. So now we say that the 1 minus alpha times 100% confidence interval for mu is given by this. All right, so this is the formula that we can use once we got the sample. And if we take more samples and use this formula to calculate all the confidence intervals, and then about 1 minus alpha times 100% of them will cover the true parameters. Okay, before we look at some examples, we would like to look at another problem. It's a very common problem. How big the sample? How big the sample should I get in order to draw statistical inference? All right. The answer is depends. All right. So there's something that we want to set as a boundary, so that within this boundary we can talk about what the sample size should be. All right. So what are these boundaries? So obviously, what we try to do is to get a sample big enough such that the error, remember what is error? Okay, just look at the x bar, for example. I want to use x bar to estimate mean mu. So naturally, I want this difference. That means my answer from the sample, that's x bar, with the true answer, the difference of it. All right? So I want the difference as small as possible. Can it be 0? How? X bar is a random variable. All right? We can only talk about this one less. This is the error, less than certain constant. All right? And this one with a name for it. This I just use E, a letter to represent. So this is called margin of error. All right? That is the error that we will accept. This one, the difference or the absolute, this is the error. So I want the error to be within the margin of error that I specified. E, I have to specify. All right. So you can say, okay, I want a difference between your answer x bar and the true answer mu, maybe less than 5. All right? Or maybe less than 1. So you can specify this margin of error. All right? So, of course, the best is, okay, I want to have almost 100% that your error will be less than 1. Can I achieve that? All right. So maybe it's too stringent. So I try to give that. Okay, I will accept if this one, the chance of the error less than my specification, my margin of error. Let's say at least greater than 95%. So in other words, I want to come up with a sample such that you calculate the X bar and then this used to estimate mu so that the error, that is the absolute difference between X bar and mu, this one will be less than some quantity that I specified with a very high chance, 95% chance. All right. So if I want 99%, obviously I need to have a bigger sample. If I want to be 100%, almost no way, right? Unless your sample size is so big, that billion, trillion, then maybe 100%. All right? So you understand the idea. The idea is that, okay, I need to specify two things. What are these two things? In order to answer the question, how big I need for my sample to achieve that criteria. The first one is the margin of error, the E. How big the margin of error that you want to take. Then the second one is the chance that the error falls less than your margin of error with certain probability. I need to specify that probability. All right. So with these two, then I can answer the question, how big your sample size that I need. All right? Okay. So this is the size of, this is the size of the error. I forgot to mention about it. It's the size. Size of the error is the difference between, the absolute difference between X bar and mu. And want that this size of error, all right, okay. So this one is well known, all right, because X bar minus mu follow a normal distribution with 0 and variance sigma square over n. All right, so it basically I divide it, then it becomes 0, 1. All right? Okay, so we arrange it, it's look like that. All right? Basically, I just multiply the sigma over root n to the other side. If I divide this by sigma root n, right, then it's sigma alpha over 2. At this point, I just want to remind you, if I say x between minus b and b, then it's the same as saying that x is less than b. Right? These two are the same. This is how we define, how we use this absolute value. So if I say absolute value is less than b, all right? What does this mean? So x can be a negative number. So the absolute value of x is still become a positive number, but it cannot go beyond b. So in other words, your x cannot be of a negative number less than minus b. It has to be between minus b and b. So that's how we get. So this one, all right, this is my sort of my x here, and this is my b. So that's for the absolute of x is less than b. Okay? So now, if I want to achieve this to 1 minus alpha, then, in other words, my margin of error and these numbers, okay, so I can put them equal, right? This side is the same thing, right? This side and this side is the same thing. So less than E, and this, I put it equal to E. But there's a minor point that you have to pay. It's greater or equal to 95%. So let me ask you. So now, how do I put E and Z alpha over 2 sigma over root n. So that 1 is this statement. All right? Probability of x bar minus mu absolute value less than E is greater or equal to 1 minus alpha. This one is equal. So now, should I put equal, greater than, or less than? Or greater, equal, or less than equal? What do you think? So you want it to be bigger, have a bigger probability. So your E has to be what? Bigger than this Z alpha over 2 times sigma over root n, or less than it. If it's equal, if this is equal, then of course E equal to this one. But now I want the probability to be bigger. So then what should I have this E? Should it be bigger? Or should it be smaller than Z alpha over 2 n minus n sigma over root n? Where's my... Of course it's bigger. You want a bigger probability, right? If I say that the chance of this random variable less than 2, all right, is 90%. So now if I want, I change 2 to 2.5. So what can you say about the probability? I say that the random variable absolute value of this random variable less than 2, all right, less than 2 is 90%. So now I ask you, what is the probability if this random variable is less than 2.5? I increase it to 2.5. So what's the chance? Smaller than 90% or bigger than 90%? Of course it's bigger than 90%. Now you have a bigger interval. All right? So in order to achieve bigger equal to 1 minus alpha, your E must at least equal to that Z alpha over 2 sigma over root n. Right? Okay. I just want you to try to be more sophisticated that you otherwise I just put equal. All right? But I want to specify my condition is that the error, the size of the error less than the margin of error with at least probability of 1 minus alpha. If I say that the probability of the size of the error is less than the margin of error the probability equal to 1 minus alpha, then I don't have to worry about which side that we're working on. Okay? So this is how we get from here. So we finally arrive at this. The E must be equal to this one. What we are trying to do? What's the initial question? What's the objective of doing all this? We want to find the sample size, how big the sample is, so that it achieves the statement. The margin of error specified and the probability of the error within the margin of error with at least a probability equal to 1 minus alpha. So I want to get n. So again, the same trick. You have to put n on one side and the rest on the other side. So you come up with this formula. All right? So n has to be greater or equal to this number. All right? So now, formula is obtained, right? But I want you to understand the formula. Your sample size depends on 3 quantities. If E is small, then your n will be big, right? So what does E small means? If E small, then your n will be big. Why? E is in the denominator, right? But what does E small mean? E is small or decreasing means that your margin of error, you said it's so small. I need a bigger sample in order to achieve that. All right, so that's how we do it. Secondly, if sigma is big, then what can we say about n? Also big. What does that mean? It means that if your underlying distribution, population with a variance which is big, that means it varies a lot. So in order to do it, to achieve the same confidence or same confidence, you need a bigger sample size because it varies so much, right? You can think of it, right? If you try to catch a fish, the fish is almost die, it won't move, very stable and no variation, very easy to catch. But if it's very energetic, then it moves around and then it's difficult to catch. So the same thing, if the variance is so big, you need a bigger sample size in order to achieve that level of confidence. Finally, how about Z alpha over 2? So remember, 1 minus alpha is our confidence. How big the confidence? So if alpha is big, alpha is small, then what is that alpha over 2? Is it big or small? So of course, Z alpha over 2, okay. Maybe let me put it this way. 1 minus alpha, I want it to be big. That means I need more confidence. All right? Then your Z alpha over 2 will also be big. Right? Remember? I want 1 minus alpha. I want this one to be big, right? You expand this one. So this point will be getting towards the right. So it's getting bigger. So this one is big. All right? Then, of course, then your sample size will be big. So in other words, if you need more confidence, again, you need a bigger sample size. All right? So my point is here, first of all, you want to find a sample size, you need to specify something. Specify, in this case, specify the margin of error and specify the confidence that your error is within this margin of error. So we come up with this formula. All right, at least n at least equal to that in order to satisfy this criteria. Then you have to understand the behavior of this. Okay, what happens if I change, or if the error, margin of error that is smaller, I need a bigger sample size. All can be obtained from this formula. All right. Okay, here's an example. I think I can leave the details for you. You just plug in the numbers. But what it means is that, okay, if I want to calculate from the sample of 36, I calculate the X bar to estimate, calculate it to estimate mu. All right, so this is the X bar, and I want it to estimate mu. All right. So sigma is known. So we want to compute the confidence interval. So just substitute in the formula. And how big the sample size, so what is n, such that 95%. So this is 1 minus alpha. I want a 95%, at least 95% that error, our estimate of mu, is off by less than 0.05. So this is the estimate minus the true answer. So off by at less than 0.05. So this is what it means. So the error of your estimate and the true parameter, all right, is less than 0.05. In part B, part 2, you need this part, but you don't need this. This one is not required. What the value of X bar is not important. The X bar equal to 3.5 is for part 1 to compute the confidence interval. For part 2, it's just a question. all right, without looking at the sample. I don't need the sample information. I just specify that sigma equal to 0.3, and I want the margin of error to be 0.05, and I want the confidence to be 95%. So you just substitute in, and you got the answer. So this is the confidence interval based on this particular sample, all right? And the n turned out to be greater or equal to 138.3. Yeah? So the answer should be greater or equal to 139. Yeah? N cannot be decimal place. It has to be round to an integer. Then why not 1.3? Yeah? Obviously, because it is greater or equal to that number. Okay, if it's 1.3, you may not achieve the specification of the confidence level. All right. So n has to be a number which must meet this lower bound. So as an integer, only 139 is the smallest integer that will be greater or equal to 138.3. $140. Is it okay? Yeah, okay, because the answer should be like that, right? Any number greater than 139, but not 138, 137. All right, how about variance unknown? So we don't know the population variance, but here we assume that we know it's normal. All right. Now, as I said, if you have large sample, it will make life much easier. So here, let's assume that the sample size is not that big and see how we handle the situation. So remember, then we have this. Remember, I don't know sigma, so I replace by the sample variance, or sample standard deviation. And ask yourself, what is the distribution of this one? So this follows a t-distribution. A t-distribution. All right? So therefore, so these random variables fall between these two values with 1 minus alpha. So I rewrite it, rearrange it, all right? And at the end, I have mu on one side of the inequality. There are two inequalities. So mu on the bigger side for this inequality, and mu is on the lower side or on the left-hand side for another inequality. So I combine them, so the probability of this random interval cover mu with probability 1 minus alpha. So that is the confidence interval. Okay, so this part is to tell you how to derive the confidence interval. So now, so remember, we are talking about the sample size is small. So small, as a rule of thumb, less than 30, we consider it small. All right, so this is the confidence interval. So it's not too difficult to see or remember. Of course, you have help sheet, right? So you can write it down. But basically, it's like this. You want a confidence for mu. The first step is to get a point estimate, to estimate mu. Next, all right, we try to construct an interval. So the interval will be some multiple of the standard error. All right. This is the standard, this is the variance of x bar. Variance of x bar. All right. So I take the square root, so we call it standard error of x bar. So we are plus or minus that. So the question is, what is this k? All right. Now, so in order to achieve that confidence level, the k depends on the underlying distribution. If sigma square is known, then this k is taken from a standard normal. If sigma is known. If sigma is not known, then we have to replace this by its estimate, s squared over n. In that case, all right, so it becomes s over root n as the square root. Then this k now becomes a t-distribution, alpha over 2. All right. But remember, so far what we discussed is assuming that you have a normal population. The data is, the sample is taken from a normal population. So, if n is bigger than 30, can I still use this? If n is bigger than 30? Yes or no? Confusion? Of course, yes. It has nothing to do with the sample size. Unlike central limit theorem, you require sample size is big. So what we need is the population should be normal, all right? And it doesn't matter whether the sample size is big or not. But here I say that the sample size assumed to be small. Assumed to be small. So because for big sample size, we can try to replace this t, this constant, by z. But this is only an approximation, and we use the central limit theorem. And not only that, the law of large number as well. All right? So for large n, then we can use this. All right, replace it by. But to me, you can still use the t. You can still use this t n minus 1 alpha over 2. I think if n is bigger, let's say 100, then it's already this value, and these two, when n is very big, these two numbers are very similar. All right. Okay. So here is an example. I got n equal to 7, so it's very small. So you cannot use the central limit theorem. So I construct the confidence interval and make sure, all right, the content, the x follow approximate normal. Approximate normal, then we just treat it as normal and then proceed. All right. So in this case, we need to have t n minus 1. This is n minus 1, 7 minus 1. All right. So we'll compute it, and here is the interval. So mu is between 9.738 and 10.262. Here, frequently I was asked, how many decimal places do I need? All right, I think usually 2, 3 decimal good enough, provided that they are significant. So if your interval, if somehow you calculate it and it turns out to be mu is between, let's say, 0.00001 and 0.00005. Oh, Dr. Sensei, it is 3 decimal places. Okay, so the answer is, right? What? Right? So, what I mean, you should think about it, at least you show some significant figures. All right? So that's not applying how many decimal places blindly. All right? So if I say 3, you just take 3. Then I don't know the answer. All right? It depends on the situation. So take significant digits so that at least it can show that there's some difference. To me, is how much you know is important. Whether your answer is exactly the same as my answer up to the 10th decimal place is not important, so long as you have done it right. All right. Sometimes there's some rounding off error, or your calculator is different from my calculator or my computer, so the answer may be slightly different. All right. So it's a second example. So okay, now this one is just more than just put in the formula. So we have a departmental store chain, and we're interested in estimating the average amount, that means the mu, of what? Of the credit card customer spend on their first visit to the mall, or to the new store in the mall. All right? And then we take a sample size of 50. And we got the x bar and the s square. All right? So we are asked, identify the population the departmental store chain is interested in learning about. What's the population? And which population parameter do we interest in or wish to estimate? And construct a confidence interval for the parameter in part B. All right. Now, okay. The population is the population is the customers, okay? The customers of this departmental store, which all the credit card customers. If you don't have a credit card, then you are not part of the population. All right, so it's those who use credit card. All right. In fact, this is what we understand by population. But in fact, what we really interest is the amount that they spend. All right? So, okay, there are two parts. When we say population, we refer to the human, the individuals. But from statistics point of view, what we are interested is not the human, but certain characteristic of these individuals in the population. So what we're interested is how much this individual spend on the first visit of the mall. All right? So it's a bit confusing, huh? A population is individuals, all these customers with credit cards. All right? But in fact, what we're interested is a certain characteristic of these individuals. What that characteristic is that how much they spend, all right, in the first visit using the credit card. All right. So then we can talk about the parameter, or we can talk about the distribution. So this, how much they spend, this amount, let me call it X. This follow certain distribution. We may assume that, did I say anything about it? No, huh? So you may have to assume that they follow normal distribution with a mean mu and variance sigma square. We don't know mu, we don't know sigma square. In fact, we don't know whether it's normally distributed or not. All right? Okay. But thanks to the central, because the sample size is considered quite big, it's 50. So we can apply the central limit theorem. So although I don't know the behavior of this X, which is the amount of money that the customer spend, but I can approximate a distribution of X bar. So N is large, so I can use this as a confidence interval. All right? So this is the estimate of sigma over root N. All right? And this one is taken from the standard normal. All right? So I don't need to know how the amount of money that they spend, how this amounts behaves. All right? In other words, I don't need to know the distribution. What is this distribution? I don't know. I only assume that this is mu and this is sigma square. All right? But this one, although I don't know this distribution, or I don't know the distribution of x1 up to xn, I don't know. But this one I know is approximately normal. All right? And we can replace this by the sample variance, the sample standard deviation. So this one again is approximately normal. But of course the approximation may be even worse than this one. All right. So that's how we get this confidence interval. All right. So at the end we come up with this. So the amount that they spend is between $58 to $67. All right. Okay. Now, instead of one means, now we look at two means. I don't think it makes sense to talk about, to find a confidence of the two means. Okay, we try to, usually we would like to know whether the two means are the same. So in other words, we would like to look at the difference. All right? You can look at the difference. And again, it doesn't matter whether you look at mu1 minus mu2 or mu2 minus mu1. You just have to adjust your formula accordingly. What I mean is it doesn't matter which one is called 1, the sample 1, and which one is called sample 2. You can swap the two, so it doesn't matter. All right? Okay, so let's assume that you have two populations with means mu1 and mu2 and variance sigma 1 square, sigma 2 square. Then, if we are interested in finding this, so the first step is to look at upon estimate. So I will estimate this by mu1 by x1 bar, mu2 by x2 bar. So I will use this as a upon estimate, upon estimator for mu1 minus mu2. So in order to construct the confidence interval, then I need to okay. What we need is that it will be something like this. For means, it will still again plus or minus a constant times the standard error of this one, which is sigma 1 square over n1 plus sigma 2 square over n2. And this is assume 1 sigma 2 known. So here, assume they are known. Then, if x11 up to x1n, all right, follow normal with mu1 sigma 1 square, x21 up to x2n, all right, okay, n1 and n2, right? Because they don't need to be the same sample size. If we have this, then this one will be z alpha over 2. All right. That means if I assume that both populations are normally distributed, then this is just the variance of this. So this one is just the standard normal, z alpha over 2. So this will be the formula for the confidence interval for the difference between mu1 and mu2, with the assumption that both populations are normally distributed. All right? So, what happens if the population, if we don't know, if we don't know sigma 1, sigma 2 square? Okay, then can I just replace this by S1 square? So this one changed to S1 square over N1 plus S2 square over N2. Then what is K? Yeah? Sorry, I don't know. But what happens if the sample size are big? If sample size are big, then both N1 and N2 are big. Then what can we say about the distribution of x1 bar minus x2 bar? It's still, okay, because x1 bar is not approximately normal. x2 bar is approximately normal. So the difference is again approximately normal. So it's just to figure out what is the mean and what is the variance. So the mean is mu1 minus mu2. And the variance, sigma 1 square over n1 minus sigma 2 square over n2. Is it correct? Is this correct? No, huh? It should be plus. All right? Don't fall in the trap, huh? It should be plus. Huh? Why? Because variance is expectation of x minus, it is something like this, have a square there. All right? So that's why the variance of ax plus by is equal to a square variance of x plus b square variance of y. And what else? There's a cross product term. Remember a plus b, the whole thing square, when you expand it, is a square plus 2ab plus b square. So there should be this term, covariance of xy. Can I remove this one? I don't like it. No, you cannot. Unless what? Unless I don't know, right? That's really I don't know. Unless xy are independent, then covariance of xy is equal to 0. So we can drop it. All right? Okay. So if sample size is big, I can still just replace the sigma 1 squared by s1 squared x2, sigma 2 squared by s2 squared, and then this k is still sigma set alpha over 2. If the sample size are not big, then this number is not so nice. So there's a way to, but it's not, we are not within the scope of our discussion. All right? But, okay, sample size is small, we still need this one. All right? Sample size is small. Okay? And let me make it easy. So assume that these are not known, unknown. All right? But we know that they are equal. Will that help? Yes, it helps a lot. Okay? Now if they are equal, then what is variance of x1 bar minus x2 bar? So it will be sigma square over n1 plus sigma square over n2, or just sigma square 1 over n1 plus 1 over n2. Therefore, if this is true, then x1 bar minus x2 bar will follow normal with mu1 minus mu2 and variance sigma square 1 over n1 plus 1 over n2. So I can standardize it. This minus the mean divided by the square root of this. I don't know sigma, right? I replace it by some estimate. Then what is the distribution? Oh, it's not this page, but then you will have this. What I say, if I continue, all right, minus mu1 minus mu2, square root sigma square 1 over n1 plus 1 over n2. This is standard normal. If I get an estimate for sigma square, replace by estimate. Later on, I showed you, I call it SP square first. So what is the distribution then? It will be a T distribution. And the degrees of freedom is n1 plus n2 minus 2. All right? Because we can show that. You don't have to worry about it, but we can show that. I will define what SP square is. This will follow a chi-square distribution with n1 plus n2 minus 2 degrees of freedom. So I just remember in chapter 5 we talked about standard normal over square root of the chi-square distribution divided by the degrees of freedom. So it looks as if I just replace the sigma by SP. Well, SP is the estimate for sigma. So here, may I ask, how to estimate sigma, which is supposed to be sigma 1 square. It can also be sigma 2 square. So for sigma 1 square, I know I use S1 square, the sample variance of the first sample. So now I have a dilemma. So I use S1 square to estimate sigma square, or should I use S2 square to estimate S2 square, the second sample variance, to estimate sigma square? Which one should I use? Take out a corner, toss it. Tail, I take first S1 square. Head, I take second sample. So of course, why I have to choose one out of two? Can I use both? How? Literally take the average, right? S1 square plus S2 square divided by 2, right? But I have a better one. Because if first sample has 100 observations, second sample has only 10 observations, which one do you believe that have a better estimate of sigma square? Both estimate the same thing, all right? So in that case, I will put a weighted average of the two, all right? So the weighted average will be something like this. So this SP square is N1 minus plus N2 minus 1S square, N1 plus N2 minus 2. All right? So if N1 is big, my S1 square is contributing more to this SP square. If N2 is big, then bigger than N1, then of course N2 minus 1 will be contributing more. All right, so here, I already cover known and not equal. In fact, it doesn't matter whether equal or not. Once it's known, it's the same thing. But here you require it to be normal population. All right? Okay. If sufficiently large, then again, we will have the same formula. So what is this formula? This is what I just mentioned. And so this is standard normal. This whole thing, standard normal. So rearrange it. So this is my answer. So you want to estimate this one. So it's the point estimate minus a constant times the standard error of this. That means square root of the variance of this one. This part is the square root of the variance of x1 bar minus x2 bar. This one. All right. So this formula applies to the underlying distribution is normal, applied to you have the knowledge of sigma 1 square and sigma 2 square. If you don't know that, then you cannot use it, right? But if the sample size is big, all right, okay, here, sorry. That's it. Okay. Oh, this part, I did not mention anything about normal. This part. I just need big sample size, all right? So I can still use this formula, okay? And why we can do that? Because of the central limit theorem. Because x1 bar will be approximately normal. x2 bar will be approximately normal. Therefore, x1 bar minus x2 bar, again, will be approximately normal. You just have to figure out the mean and the variance. All right? Okay. So you see the difference between these two. If you have this normal, the metric word normal, you can use this formula. It doesn't matter what your sample size is. But if you don't have this magic word normal, you need big sample size in order to use this formula. This formula requires the knowledge of sigma 1 square and sigma 2 square. All right, so we apply to this example 1. So I leave it to you. Again, I want to find the confidence interval with mu b minus mu a. So this one specify which minus which. All right, But if you just ask for the difference between the two population means, so it can be mu A minus mu B. All right? It doesn't matter. You just make sure that you know which one is A, which one is B, or which one is first sample and second sample. Your answer will be just the same as this after hard work. So we got this as, so this is mu B minus mu A. So this is the confidence interval. But if you want to have mu A minus mu B, so what is the confidence interval? How to get from here to here? I just multiply by minus 1 now. So I multiply minus 1 to this. So I got mu A minus mu B for this side. This one becomes minus 3.428, right? And why I have to write it over there here? Because once I multiply negative 1, minus 3.428 is bigger than mu A minus mu B. Right? Hey, multiply by minus 1, you have to reverse the inequality. So similarly, this one. So that's what I mean by, it doesn't matter which one minus which. The answer will be the same. I mean, same means that you will get the correct answer. It doesn't matter which one minus which. All right, they're equivalent. They're equivalent. All right, so how to get this answer? So we just apply the formula. You have to identify what is XA bar, what is XB bar. And in this example, we know sigma 1, sigma 2. Pay attention to what is given to you. Here, it's not sigma 1 square, it's sigma 1. Sigma 2 equal to 8, sigma 1 equal to 6. All right? And we want 96% confidence. So each side is 2%. So this is the number. And, okay. So how about the case when the variance are known? So if the sample size is big, all right, so because sigma square is not known, so I replace it by S1 square and S2 square and proceed as it is normal. All right, so the confidence interval for this one is very similar to the previous formula. We still have this, but this one is replaced by S1 square. This replaced by S2 square. All this, okay, is valid because of the central limit theorem. Big sample size, all right, and the S1 square is considered as very good estimate for sigma square. What I mean good is that this S1 square and sigma 1 square, the difference of these two is very small if your sample size is very big. All right, so that's what we try. So that's why we don't know sigma 1 square, so I try to use the best known or guess that I can use. I use S1 square, provided that your sample size is big. All right, so I apply to this example. So I have two, each one is quite big, 50, all right, for N1, for sample 1 and 50 for sample 2. So this is XA bar, SA, all right, XB bar and SB. And we want 95% confidence for the difference population means. I did not say which is which. So you can have mu A minus mu B or mu B minus mu A. It doesn't matter, all right? The answers will be just, you multiply by -1 or swap the both ends by multiply by -1. All right, so with all this, substitute in the formula, because the sample size is big, so the constant that we use is from the standard normal distribution. So here is the answer. So it is like this. So if you try to look for mu B minus mu A, if you do it correctly, the answer will be 6.564 and 11.6. It will be like that. You just multiply by minus 1 to all these two inequalities. So in other words, it doesn't matter. All right. But read the question carefully. If the question asks you to find a confidence interval for mu B minus mu A, you should give a confidence interval for mu B minus mu A. All right. If you just give me a confidence interval or the other way around, you have not complete answering the question. But if you did not mention which minus which, just say that the difference between two means. Then it doesn't matter which one minus which. So, unknown but equal variance, all right? Like in that case, I still need normal. Sample size not big, all right? Then, because the same, so I have this one, all right? They make life easy because now I don't have sigma 1 square and sigma 2 square. I just have sigma square so that I can still apply the t distribution, all right? Without that, if it's sigma 1 square and sigma 2 square, it's more complicated. All right, so this follows a standard normal distribution. Now, I try to estimate. So this is a weighted average. Weight n1 minus 1 over n1 minus 1 plus n2 minus 1 to this one. And the other is the weight is this divided by this. So that is the estimate for sigma square. Why I use that? Because that is the best. I mean, the sample size big, I give more weight to that estimate. If n1 and n2 are the same, then this is just s1 square plus s2 square divided by 2. If they're same, then sp square is nothing but just s1 square plus s2 square divided by 2. Divided by 2. Right? So, this is nothing but just n1 plus n2 minus 2 times sp square over sigma square. Follow a chi-square distribution. All right? Remember we mentioned, we know that this is a chi-square with n1 minus 1. This is a chi-square with n2 minus 1. They are independent. So when I add them together, it becomes like that. It's equal to a chi-square distribution. And degrees of freedom is the sum of these two. All right? So here is the... So I just replace the sigma square by sp square. It looks as if I do that. Then follow a t distribution with n1 plus n2 minus 2 degrees of freedom. So from that, this is the confidence interval. All right? This is the constant, and this is the estimate of the variance of x1 bar minus x2 bar. We estimate it. Replace the sigma by sp. You see, the form are very similar. You just have to make sure that you know what this is, what this is. So this mainly depends on this one. So what it means, under what condition you have this. So you have sp because sigma 1 square and sigma 2 square unknown to you, but they are equal. If both are known to you, then you don't use this formula. You just substitute the sigma 1 square, sigma 2 square, and the constant becomes from a standard normal. All right, so here it is. So if it's a sample size is big, then this one I can use the one from the standard normal. All right, because the t distribution getting closer to standard normal as the degrees of freedom getting bigger. So in that case, because of this, so now I replace the t with a z. And the example, so I leave it to you, right? So this case, n1 is small, n1 is 12, n2 is 10. So where's the equal variance? I need to assume two things. normally distributed, at least I don't say exactly normal, but then I say approximate normal. So you just treat as normal. And the other condition, so this is condition 1, this is condition 2, in order to apply the formula. All right? I don't know sigma 1 square. I don't know sigma 2 square. But I know that they are equal. All right? And I also have normal population. All right? So substitute in, and then you get all this, or you compute the SP square. All right? And then you construct the counter. So this is x1 bar minus, okay, so this is x1 bar minus x2 bar, and this is the t, and this is the standard error of this, or estimate of the standard error. So we just change plus, then this is the upper limit. All right. Okay, so this is t n1, n2 minus 2 with 0.1, 0.05, half of the 10%. Oh, n1 is 12, so this is 20. n1 is, this is n2. All right, so it's 20. All right, so substitute in, and you got the difference is, the confidence interval is between 0.693 and 7.307. If you start to consider mu1 minus mu2, all right, then this will be minus 4 instead of 4, and the rest are similar. So the answer will be, all right, minus 7.307 and minus 0.693. All right. Now one more thing. This interval, from based on one sample, this interval, does this interval cover 0? It does not cover 0. Right? It's between 6.693 and 7.3. It does not cover 0. So what does it mean? We are quite confident, based on this sample, or the way that we do construct this confidence, we are quite confident that the mu may not be 0, because this interval does not cover the 0, does not cover 0. All right? So that's one way to, alternative way to interpret this confidence interval, whether mu1 equal mu2 or not, or mu1 minus mu2 equals 0 or not. Because it does not cover 0, so we believe that it may be mu1 minus mu2 may not be 0. Because we are quite confident that it should be some covered by this, all right? And this does not cover 0. Okay, so I think I have to stop here. I will continue next week.